All right, so the last part of our discussion on power supplies have to do with protection circuitry. And we'll talk a little bit about that. And then there are some things that you will answer when I put together the sort of tutorial questions for you. So here we're back to our regulated power supply. We have the error amplifier in there. Right, so we have the feedback regulator here. What happens if RL short circuits? In other words, RL starts to get very small. Right now, those are the kind of things that happen. You're working in the lab and you're wiring up the breadboard. You have the power supply on and you didn't notice. And as you're hooking up something, the two wires touch. So the load, what was supposed to be the circuit load, becomes basically 0 ohms. So what happens in this circuit? If I put 0 ohms there, what is going to, the circuit is going to attempt to supply the current to 0 ohms, which is a very large load. And of course, this transistor is what is taking that. So as RL goes to 0, the current through this is going to go up very quickly. And if the transistor can't handle it, the transistor is going to burn. All right, so you're going to blow the power supply. So what we need to do now, and that is not good design. You never have a design where your components, in the event of an accident, an accidental failure, right, that the electronics, you try to build in protection circuitry as far as possible. Okay, of course, one way is that on the unregulated side, a very simple way is to just simply put a fuse, so that if I'm designing this, and in any case, it's always good practice. So if this is supposed to give 1 amp DC at maximum, what I do typically on this side is to put something like a 2 amp fuse. Right? Why you wouldn't put 1 amp is sometimes when the circuit turns on, it may take a little more than 1 amp drawing through it. And then, so at that point, if you had a 1 amp fuse, it will blow. So typically what you would do is to put maybe a slightly larger rating for the fuse, so that in the event that the load, in this case, short circuits, if the load short circuits, then as soon as the current through TR1 passes 2 amps, then the fuse blows and the entire the power supply shuts off. And of course, if this is passing 2 amps, remember we said this is, across here was about 7 volts. 7 volts at 2 amps means that the transistor, until that fuse blows, the transistor has to handle about 14 watts. Okay, otherwise it is going to burn. Now this is absolute protection, and is always a good idea to have a fuse in the circuit somewhere. You can have the fuse on the secondary side. You can have the fuse on the primary side of the transformer as well, right? Remember, if you're taking 2 amps on the secondary side of the transformer, you could calculate how much current you're going to take on the primary side, and you could put the fuse accordingly on that side. All right, but no harm in having a 2 amp DC fuse on the unregulated DC side. And in the event that something happens, it burns. The problem with this, of course, is if you make a power supply and you have it in a nice case, you're going to have to open the case and take out a fuse every time this thing happens. So you want something a little more elegant. As an engineer, you want something a little more elegant. Can we make this circuit protect itself? And the first way we can do that is to insert another little transistor into the circuit. So let's look at this character here. Notice what we've done. We've inserted another transistor. So in the output line from before, all right, let me just clear this thing. Right in this, on this nice, the line leading out here, what we've done is that we've put in a resistor now. So we put a resistor, we put a transistor inside of here. And notice how transistor is wired, the transistor is connected between the unregulated supply and it's going to the base of TR1 again. Right? Remember the important thing, we could always control TR1 once we can control this voltage here. Right? So the control voltage for TR1, right? Draw a line. The control voltage for TR1 is at this point in time. If we move that voltage up and down, we are able to make TR1 turn on and off. The regulation part does that through TR2. And now we're putting in another circuit with another little transistor in it. And let's see what that does. So how this works, the load current is passing through R4. I'm just zooming in here. Remember? Oops, sorry. Remember here, this is IL. Right? So the load current is passing through R4. As the load current increases, eventually the voltage drop across R4 is going to get greater than 0.7 volts and turn transistor TR3 on. Once that turns on now, it's going to start, remember the TR1 is going to start taking base current this way. So it's going to draw the base current drive from TR1 as well. And again, the other great thing about this is that once TR3 turns on, there is a fixed voltage across here all the time, 0.7 volts. Once this transistor is on, you always have 0.7 volts here. So it's acting like in other words, almost like a small Zener diode at that point. So if I have a fixed volt across R4, it means at that point in time now, regardless of what is happening elsewhere, R4 will only be allowed to pass a certain amount of current. And it doesn't matter what is happening elsewhere in the circuit. Fair enough? Everybody getting that? Right? R4 is biased. Once the current through R4 gets enough to turn on TR3, then once that current is flowing, R4 is now biased by a constant voltage. In other words, the supply has now entered a constant current mode, and it is limited by IL. At that point now, if you go back to the output here, so we've started to increase IL. This is, well, IL is really going here, right? IL goes here. So I've increased IL. R4 causes TR3 to turn on so that the voltage across RL is fixed at 0.7 volts. So the current through RL is now fixed. So IL starts to become constant. Right? As IL starts to become constant now, we are also pulling current away from the what do you call it? From the base of the TR1. So IL is constant, but TR1 is slowly turning off. So V out starts to drop. And in fact, when you look at it now, right, what you get is this sort of behavior. So you have V out, you're supplying V out, and this is the current along this line. So you're supplying V out at a nice current, and then at some point in time now, TR3 starts to turn on. So as TR3 starts to turn on now, TR3 is diverting current away from the pass transistor. So the output voltage starts to drop. But because TR3 is in now a constant current mode, the power supply keeps supplying that, and slowly it supplies the voltage at a constant level until eventually Vout drops to nothing. All right? And the power supply shuts itself off. So it can never supply more than IC max, but the voltage At this point in time, you will suddenly see a voltage if you're designed for 12 volts, and this happens over a short period of time. It's not something that's going to be continually happening. You will see the 12 volts going nice, and then as you approach whatever is the maximum limit, in our case, let's say it was a 1 amp supply, as you approach the 1 amp, you design that. At 1 amp, now you have 12 volts. As soon as you go beyond 1 amp, the current is clamped to 1 amp, and then the voltage starts to drop from 12, and it quickly goes down to 0 until you remove the load, whatever is causing the load to pull that much current. All right? And you design for it. So how we design, of course, you always use a worst case scenario. What is the maximum load current that I'm designing for? In our previous example, the maximum load current was 1 amp. So in other words, the voltage drop, of course, R4 is 0.7 volts. So if it's 0.7 volts, then I load times R4 must be 0.7. You solve that, and you get that R is 0.7 ohms in this particular case. And you get those are the small, what they call small wire wound resistors. They look like a little, sometimes you see them in the lab, they look like a little bit of ceramic, like a little ceramic rectangle. They're designed to carry, because it's carrying, remember, it's carrying current to 1 amp, so I squared R, so it's going to get warm, all right? But the actual value is extremely low, right? So that's one type of very simple current limiting device. So you put the current limiting resistor in it, the resistor turns on the transistor and as soon as you exceed your current supply, or your design supply rating, the system automatically goes from a constant voltage regulator to a constant current. So it supplies a constant current and the regulated voltage. If you try to take more, the regulated voltage just keeps dropping until it goes to 0. Right? Hopefully by that time, you would have realized something going on. What some people do in their design is to put something like, I don't know, you would have met it before, something called a light emitting diode. Yeah? You put a light emitting diode in the circuit with TR3. So when TR3 turns on, the light emitting diode lights. So you see a little light on your panel coming up and saying, well, wait a minute, something happened here. And you switch off the supply and go and check what the fault is. Right? So everybody all right with that? Make sense? And notice the little yes question.
So I understand the concept for the most part, right? But if we take a look back at this slide with the previous slides, with the circuit itself, right? So essentially what is happening when the current starts to increase, the IL, sorry, when it starts to increase, it passes through the TR1, R4, then it would go down to the TR3, turn it on. When TR3 is turned on now, it starts to pull current from the base current now. So it would take from the TR1. So essentially that limits what goes through R4.
Right. So the point is you're forgetting this device here. So when the power supply is now turned on and IL is 0, you have 12 volts here, you have nothing flowing here, right? TR3 is off and the power supply is sitting down. If I take half amp, right, 0.5 amps, oops, zoom that up a little bit. If I take 0.5 amps no, from the power supply, R4 I calculated is 0.7. So 0.7 by 0.5 is 0.35 volts. So TR3 doesn't do anything. It's still off. So all the way up until the 1 amp. So at even 0.9 amps, right? 976. So we have about 0.6 volts here. So TR3 is still off. And all of that current is supplying, as I say, through TR1 and is going to the load. I now reach 1 amp. At 1 amp, TR3 now gets 0.7 volts across the base emitter junction. So TR3 now has started to turn on. Right? It starts to turn on and it's taking some current this way. Right? The current is going here to the power supply as well, a small amount, and the power supply is supplying 1 amp. If the power, and at that point now, because this transistor is turned on, R4 is now biased by 0.7 volts alone. So it doesn't have a choice, just Ohm's law. Ohm's law will not let any more current than 1 amp pass through R4 now, because it has a constant voltage across it. Yeah?
Yeah.
So we're absolutely limited to 1 amp through R4, regardless of whatever else the circuit is doing. So if I was to short out the load, the short out load will try to take more than 1 amp, but R4, because it is limited by the fact that I have 0.7 volts here and it can only pass 1 amp, will not let that happen. And any excess current for the time being, for the brief while, any excess current that is attempting solar for a brief while, let's say I short circuit that. So this is going to take something significantly greater than 1 amp, or try to.
Right.
This is limiting 1 amp, and for a short period of time, the load wants significantly more. So what the transistor now is going to do is to pull the extra current away from the base of this and turn TR1 off. It doesn't have a choice. That's just the basic circuit operation now. This is limited. The voltage across here. Here is not, oops, here is 0.7 volts. Okay, for some reason I'm not getting it on right. Here is 0.7 volts. So regardless of what is happening here, up until a short circuit, this will always remain at points, at what do you call it, 0.7 volts, and therefore only allow that 1 amp to pass.
Right.
Yeah?
Right. True.
Yeah?
True. Makes sense. Right, thanks.
What some people don't like is this, the behavior at this point in time, right? What some designs do is that they in fact, what most people with high grade power supplies, what they would do is that if I set it for some output voltage, that it does that, and then the instant it reaches whatever current I have, it just shuts off there and then. It doesn't sort of fluctuate around the place and the voltage goes up and down. I want the voltage up until the rated value and then shut off. And there are ways to do that. But it's a little more complex, and it's not really part of our discussion here. Okay? So at this point in time, there's a little bit of what they call soft regulation. So the output voltage is varying from the 12 volts a little bit. Right. So here's an addition now to the previous circuit. Because of this characteristic, let me just clear this note. Again, for safety's sake, we have, you remember, we have that TR, although we're limiting the current, the pass transistor still has to contend with it. So until you turn the power supply off, the transistor has to still keep passing this load current, which is 8 watts in our design example, and it could be more around the place. So what a version of this does is that not only limits the current, but it reduces both the current and the voltage. And this is where the other little protection circuit comes in. So here, just like before, we have R4 and we have TR3 again. So the process is essentially the same from that part. But then what we've done is that we've added a little, instead of the base of the TR3 being connected directly to resistor R4, we put in a little potential divider of 2 extra resistors, which are R5 and 6. Yeah? Fair enough? So what happens is that if TR, now let's look at some voltage behaviors here. Right? Once the power supply is off, once the power supply, put this here, once the power supply is off, sorry, once the power supply is working and TR3 TR3 is off, then this voltage here at this junction is equal to the voltage at the output. There's a little voltage drop across here, but remember we said if this is 0.7 ohms, for instance, right, and we're taking the current and we're working at 0.5 amps, right, the voltage drop across R4 is going to be 0.35 volts, which is very small. So for all intents and purposes, once the transistor TR3 is off, V out bar and VO bar and V out. Sorry about that. I should have used VO instead. But anyway, V out here instead. V out bar and V out are approximately the same. Yeah. What happens is that at the point in time now when we turn on the transistor TR3, so we start to increase the load current and eventually TR3 turns on. The same behavior happens before. Once TR3 turns on, a fixed 0.7 volt appears here. Yeah? But notice where the 0.7 volts is now appearing. Instead of the 0.7 volts being across R4 alone, like in the previous design, it is now across R4 and 5. Yeah? So because of that now, we have a little extra equation here. That the voltage here at this point in time, remember, so the voltage difference Vx here and V out here, that is 0.7 volts now. So Vx minus V out is 0.7. And on top of that, we know that V out prime here is equal to this voltage. I should have put VOUT here, right? Instead of this. The voltage V out prime is equal to V out plus the little voltage on IL and R4. Yeah? Here is a little bit bigger than here. Everybody following? Yeah? Simple circuit analysis. So how does that help us? How does that help us? Well, if the load current starts to increase, because the voltage is now appearing across here, right? The 0.7 volts is now appearing across here. If the load current starts to increase, then it causes, well, first off, we know if the load current increases because of the drop across R4, here goes down. If here goes down, here goes down. And if here goes down, here goes down. All right? So this is a type of thing, again, we mentioned it yesterday. This is another example of feedback. So in this particular case, because we've put we now applying the constant current across two resistors now, as the output voltage drops, the voltage across the appearing now at the base of the transistor is going to fall. But we are constrained by this. Again, we're putting this is fixed. So if this drops, because this is fixed, this must drop as well. It doesn't have a choice. And when you do that now, you get the characteristic looking like this instead. Remember the previous one did this. Because we have this little circuit that is controlling Vx now, and Vx is directly related to V out because of the bias voltage here now. What is happening is that as we approach the current shutoff point, the limit that we designed for, instead of following the green line, the current characteristic follows the red one. So not only is V out dropping, but the load current starts to drop, because if the voltage drop across here varies. Let me just clear that up a little bit, right? if the voltage drop, since V out is dropping and V out prime is dropping, right, leading everybody to think we have this 0.7 volts here. The current through this now, as these things start to change, the current through R4 is going to change as well. It's no longer fixed because we have another resistor in the circuit. So it's going to vary, and instead of staying at the constant value that we had before in the previous example, it's going to back up now. It's going to start doing this. So the current drops and the voltage drops instead of doing that behavior. So the pass transistor now has to carry a lot less current, or carries less current than in the previous version. And we call this particular type of protection fold back because the characteristic is folding back on itself. Yeah? Make sense? Yeah, maybe? It's quite ingenious when you think about it, and everything really comes back to, when you go back to this circuit, all of this, all we have done in, since yesterday and today was to take the basic Zener circuit. We take the basic Zener and the pass transistor. Right? We boosted the what do you call it? The capability of the pass transistor and insulated the changes of VBE by putting in an error amp so that it tracks the output voltage now, and if the voltage goes up and down, the error amp tries to correct for it. And then to protect it now from short circuits, we put in TR3. And to protect TR1 further, we put in an extra resistor divider here, so that when the thing shuts off, it reduces the voltage and the current at the same time. VI is the power dissipated by the transistor, so we're shutting both of them down together. Yeah? So very ingenious, and again, when you think about it, we're looking at it from an analysis point of view. I'm giving you the circuit and we're analyzing, but I always want you to think about it. If you were given a challenge, well, how do I design a circuit? Somebody gave me that problem. How do I put in some short circuit what do you call it, protection to a power supply? And without giving you a circuit, you have to know now, well, what does it, how do transistors operate? What turns them on? How do I measure a current? You know, that kind of thing. And that is where we like to get to at the end of all of this. Right? So not only simple analysis, but designing it. All right? And these are some of the, does it have a different application than the circuit without, sorry, just let me put up that question again. Does the protection have a different application in the circuit without R5? No, it's just a different, it protects exactly the same way. Both of them are limiting the current. This one is doing it a little bit better because it not only limits the current, but it reduces it. So that the pass transistor, until you switch off the power supply, the pass transistor has to handle less wattage. But they're both doing the same thing, which is to prevent the power supply from failing if there is something like a short circuit on the load. Right? So one is a little bit better than the other. Right? So here are the design equations for this. And the basic approach to it, so if you could read the equations, it's very simple. There's a little shorthand that we use here. We're using a Greek letter rho to represent the ratio of R5 and R6. So that particular voltage Vx is V out divided by R5 plus R6 multiplied by R6, and we call that ratio rho. And if you plug it into one of the previous equations that we had some slides ago, if you plug that rho value into this equation here, equation 2 that we have on this slide, if you plug rho into that, then what you get is that rho is this Rho depends on V out and R4 in that way. So if I design, so for instance, my previous design had R4 as 1 ohm and IL as 1 ohm, V out is 12 volts. So I could work out that rho, which is the relationship between R6 and R5 and R6, is some particular value. And like we did with a previous example, the design, how you design this is, first off, you choose what your current limit is going to be. So the example that we were carrying through since yesterday was that the design limit was 1 amp at 12 volts. So IL is 1 amp. And you choose R4 on the equation that we had before. So you can choose R4 till limit. Now R4 is in the circuit itself. So you pick a value for R4. So let's say a 1 ohm. So we choose here, we choose IL, which is 1 amp. And we choose R4 this case, which is 1 ohm. Right? We're not calculating R4. In the previous case, you had to calculate R4. Here we're going to choose R4. Once you choose R4, you go back to this equation. So I know IL, I know R4, I know this. So once I know that, I could calculate the value for rho. And once I calculate the value for rho, I now go back and I choose R6, pick a nice value for R6, convenient value. Okay, bearing in mind that every resistance here, this resistor, this resistor, this one, they are all taking current from the power supply, from the regulated side of the power supply. So if you design for IL, you want to make sure that all of the currents taken by resistors 1, 2, 5, and 6 don't take anything significant. You want them to be taking in the order of a couple milliamps kind of thing. All right. So you choose R6 relatively big. So you want something maybe in the 5K, 10K region. And then once you know rho and you know R6, then you could calculate R5 and you put it in there, and that is a power supply. The other part of it, of course, with the power supply that we said yesterday, you spec out the transistor now, the power rating of the transistor, and then you go back to the unregulated supply and you spec out the diodes and you spec out the current carrying capacity of the diodes or the bridge rectifier and the voltage on the filter capacitor, and of course you pick your D here. Right now, one of the things I'd like you to do as you go through, and just to make sure it makes sense, or to see if I may have omitted anything in the discussion, is to try and vary it a little bit. So we have been at a diode value since yesterday to today of 7 volts. Change V out. So try a different value of V out and use a radically different value of the diode, and see, recalculate everything and see how the thing works. And what you can do, if you go back here, I want you at this point, you could take this thing, and this I'll put this as one of the sort of power supply, sorry, one of the tutorial questions. At this point here, let's say you calculate it for some IL value. You calculate V out. V out is supposed to be at some IL value. So you look at it and you see what the current is at that point. You increase the load current up until it crosses the design value and see what the voltage and the current looks like. And finally, at this point, when you have 0 voltage output, what the current through the pass transistor looks like, and see what the sort of behavior of this circuit. Verify it for yourself. Okay? Right, so any questions? The ratio R5 to R6 would be 1 minus, well, is the other way wrong that we normally do it. So it's R6 over R5 plus R6. So yeah, you could flip it over. All right. So any questions? So what we have, I have the slides are up. The power supply handout with the writing is up, and there's quite a bit of stuff in there, but I'll sort of pick it up. I'm going to developing a little problem set now to check some of this thing that I'll do over the next few days, and hopefully by the time sometime over the weekend I'll have it available for you to check some of these things and maybe to ask you some other questions. You have the handout on the regulated, the three terminal regulators as well. So there's a lot of information inside of there. We have the slides that summarize this stuff, but it's always good to read in between. And if you notice, as I did, there are some little typographical errors in the power supply, the handout as well. Ask me about it or see if you can pick them up, or if something just plain and straight doesn't make any sense at all. All right, once you do that, then I think you're good to go. As I said, my intention at the end of this thing was that at this point in time, if you sit down and I give you a design, or you have some circuit to power, or you have some device that you have to make a regulated power supply to do, that you are now in the position to design one on paper that can give you a certain amount of voltage and a certain amount of current, and also protect against short circuits now, and basically the transistors wouldn't burn up. The diodes and the rectifiers would not burn up. The capacitor will give you the kind of ripple that you want, and all of the transistors will operate well within the operational zone that they're designed to do. All right, so that's the intention. So your job now is to try and review these notes and think of any questions that you have. I'll give you that problem set for revision, and we'll have a tutorial session in some time to go through the solutions as well. Yeah? So any last minute questions on this? Okay, and notice this sort of approach I'm still figuring out. The best approach is more of an, we look at the circuit and we analyze how the circuit works, and then we use that now to design the circuit. Occasionally, and hopefully, as I said, towards the end of the course, we might be in a position where we could give something without having the circuit, and let's see if we can design something more or less from scratch. All right. As you go along here, I don't know how many of you all downloaded Multisim already. Many of you all have downloaded it or asked to download it for any reason. Okay, so if that's the case, so let me see if I think we have to work out something with Mr. Hall to refresh the licenses for you all. Right. So what we could do is to use Multisim as part of the sort of virtual environment for this, to put the power supplies or the power supply design up in it, and you can vary the parameters and see exactly what happens. Okay, so that's I'll try to work on that and see if we can fit it in somewhere. So you can have that as homework. Use the Multisim as a homemade lab, a simulation lab that you could try some things with, and you can see what happens or what doesn't. Yeah, and try out some of the things that we were doing here. Okay, so at that point I'll stop the recording here.